Hey everybody, today's video is going to be about the golden ratio and the Fibonacci sequence. But we're going to start with focusing on the golden ratio and what it is. For this video, I'm going to be using this symbol. So to start off, I have a quick question here. Find a number such that squaring it is the same as adding 1 to it. So it's not obvious on top of your head what this number is going to be, but we can solve it quite quickly. So it's going to be some number, x, where when I square it, x squared, it's the same thing as if I added 1 to it. So x squared is the same thing as x plus 1. Now, I'm going to subtract x and 1 from both sides. And I'm left with a pretty easy to solve polynomial. So I'm going to do I'll just solve it really quickly. So negative b is 1 plus or minus the square root of b squared, which is 1, minus 4a, which is 1, times c, which is 1, negative 1, over 2a, which is just 2. It's going to equal 1 plus or minus root 5 over 2. And that is the answer to the problem. So 1 plus or minus root 5 over 2 is going to give you the same number when you square it as when you add 1 to it. Now, notice I said plus or minus, so there's two numbers here. This video is going to be focused on the plus version, and I actually prefer to write it as root 5 plus 1 over 2, but it doesn't actually matter. And this number is the famous golden ratio. I'm gonna leave that here somewhere, so we'll write around here, golden ratio equals root 5 plus 1 over 2. Alright, I've got another question now. Imagine I have a line, and one section of the line has length A, and the other section has length B, which means obviously that the entire line's length is going to be A plus B. And let's say, for example, that instead of A, I'm just going to call it 1. So we're going to say 1 plus B. Now, for what value of B is it true that the ratio of 1 to B is the same as the ratio of B to 1 plus B? So what I'm saying here is that the ratio of the red to the blue is the same as the ratio of the blue to the red and the blue combined. Well, let's solve it. We're comparing two ratios, so let's just write them both as fractions. So let's make this 1 over b, and let's make this b over 1 plus b. Multiplying both sides out, we're going to end up with, on this side will be 1 plus b equals b squared. And this should already look extremely familiar. Looks like I'm squaring a number on one side and adding 1 to it on the other side. And again, this means that B is going to be our friend, the golden ratio. Kind of weird. Two problems that don't really seem related to each other, but they give the exact same answer, which is square root of 5 plus 1 over 2. Now I'm going to talk a little bit about the Fibonacci sequence. Now, for those of you who don't know the Fibonacci sequence, it's quite straightforward. It's a sequence of numbers such that the first number in the sequence is going to be equal to 0. The next number is going to be equal to 1. And from then on, you're going to get the next number. So formally, we're going to say for all n and the natural numbers, f of n, which is the nth Fibonacci number, is going to be equal to the last two numbers added together. So f of n is going to be f of n minus 1 plus f of n minus 2. So you get the next sequence, the next number in the sequence by adding the last two together. So we can go through the first couple quite easily. So 0, 1, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, then 8, 13, 21, 13 plus 21 is going to be 34, 55. I think the next one will be, I believe it's 89. Yeah, we'll stop there. These are the first lot of Fibonacci numbers, and they're going to keep going. Now the Fibonacci numbers come up a lot in like art and fractals and stuff, so you'll be very familiar with the Fibonacci sequence, especially it comes up all over the place, you know, counting the petals on flowers and stuff. That's not really what this video is about, but the Fibonacci sequence is a very interesting topic on its own. What I aim to discuss in this video is how the concepts of the Fibonacci sequence, the sequence here, and the concept of the golden ratio are interlinked. And they actually kind of describe the same thing in math. What I aim to prove in this video is that if I take two side-by-side numbers in the Fibonacci sequence and compare their ratio, so here it's going to be 1 over 2. Then I keep going, so like maybe if I go to these two, this is going to be 8 over 13. If I take these two, it's going to be 55 over 89. And my claim is that the further I go this direction, when I take two consecutive Fibonacci numbers, their ratio is going to get closer and closer to the golden ratio. We're going to be approaching this golden ratio. So let's quickly formalize what that means. So I'm going to talk about a limit here. The limit as n goes towards infinity. So this just means as n gets bigger and bigger and bigger, I'm conjecturing that the ratio of two consecutive Fibonacci numbers, which I can write that as f of n over f of n minus 1, is going to reach the golden ratio. I'll say equals the golden ratio. Now, one thing to say about limits is that there's a whole conversation about series that can either converge or diverge. Converge basically just means that if I keep this limit going, I eventually will stabilize at a certain number. So there are some famous series that we know converge, like for an example, these geometric series, like if I say 1 over 1 plus a half plus a quarter plus an eighth plus, if I add all these numbers together, it's never going to go above 2. In fact, we can sort of say that it equals 2 and it goes on forever. This is the sum for n starting at 1 to infinity of 1 over 2 to the power of n. This is a converging sequence because there's a value that it will never go above. Now there are some sequences that don't converge, they diverge, which means they're going to shoot up to infinity. Like for example, the sum of the reciprocals of all natural numbers. So a half plus, so 1 plus a half plus a third plus a fourth plus a fifth. It really looks like this series is slowing down, but in fact, all you need is enough numbers, and this doesn't really have an answer. This doesn't have a limit. It goes to infinity. Now I can tell you that this limit is going to converge, which is why I'm allowed to say it equals something. Just to get that out of the way. So I'm going to show that this converging sequence happens to converge at the golden ratio. So let's begin the proof. Well, I'm going to create some more terminology here. Let's just let R mean ratio, and I'm going to say that R of n is going to be equal to f of n over f of n minus 1. So I've reframed the problem to say that I'm examining the limit as n goes to infinity of R of n. This is what I'm trying to investigate now. Alright, so with that in mind, let's take what we know about the Fibonacci sequence, namely this fact here, and let's do something to it. We're going to do a bit of rearranging. Well, I'm going to take this fact here about the Fibonacci sequence, and I'm going to divide every number in it by f of n minus 1, which I'm allowed to do. And you'll see where I'm going with this. It's not obvious that this is what you need to do here. I'm just walking you through the proof. So it's going to end up with 1, because I've divided it by itself, plus f of n minus 2 over f of n minus 1. Cool. So we end up with this. And the reason I've done this is because notice that this thing here now is the same thing as what I've called r of n. This is the thing that I'm trying to solve for the limit of. So I'm just going to sub in r of n. So we have now that r of n equals 1 plus f of n minus 2 over f of n minus 1. Now so far, so good. We've done a bit of simplification, but this fraction here is quite ugly. It's not really clear what we have to do with this fraction. But there's a solution, and I'm going to bring it down here. We're going to play with it a bit and see what we can do with it. So we have f of n minus 2 over f of n minus 1. Now, there is a rule in algebra that you might be familiar with to do with reciprocals. So a reciprocal is when I divide 1 by something. So the reciprocal of n is 1 over n. One thing you're going to have to do in math is if you take the reciprocal of a number twice, you end up with the same number. So I'm going to take the reciprocal of this number 2 times. So with a fraction form, you can just flip the denominator and the numerator. That counts as a reciprocal. So this can become f of n minus 1 over f of n minus 2. And then I'm going to take the reciprocal again. And this time, I'm just going to do my 1 over n thing. I'm going to go 1 divided by this big thing here. And hopefully you can see, this is a bit of algebra, but if I get rid of this middle step, these two things are equal. So f of n minus 2 over f of n minus 1 is the same thing as 1 over its reciprocal, f of n minus 1 over f of n minus 2. The reason I've done it this way is because f of n minus 1 over f of n minus 2 looks eerily familiar. It looks kind of like my term Rn, but with one thing replaced. So R of n is with an n and an n minus 1. This one's got an n minus 1 and an n minus 2. So instead of being R of n, this thing here is going to be R of n minus 1, because I'm plugging in different values for n. So with all that in mind, this here is going to become R of n minus 1. Cool, so I'm going to rearrange my formula a bit. I'm just going to delete some of this stuff. We'll go back to these ideas here. So we've now decided that, I'm going to go this way, R of n is equal to 1 plus 1 over R of n plus 1. Alright, so we're still at a spot where it's kind of hard to see what to do next. But keep in mind what we're actually trying to solve here. We're trying to solve for a limit as n goes to infinity of R of n. So let's assume that that limit exists. So assume there is a limit, and we're going to call it L. Because we're talking about n going to infinity, that means that when I solve for L, it's going to be equal to R of n. So L equals 1 plus 1 over. And because n's going to infinity, there's no meaningful difference between n and n plus 1, right? N is going to get so astronomically big, it's going to shoot off into space. So R of n and R of n plus 1 at this size, we can treat it like the same thing. So actually I can just write L equals 1 plus 1 over L. And again, we're assuming there's a limit here. And we're solving for L. We're going to solve for L. So I have L equals 1 plus 1 over L. We've got a fraction here, so let's times everything by L. We end up with L squared equals L plus 1. And you might be able to see now what I'm getting at. This is the third time in this video this equation has shown up. This is my number, such that when I square it, it's the same as adding 1 to it. So if I go through that process that I went through at the start of the video, I will find that L equals the golden ratio. And that completes the proof. So we've now shown that for the Fibonacci numbers, as we go on and on and on and on, the ratio of 2 consecutive Fibonacci numbers approaches the golden ratio. And yeah, I thought that was really interesting. So Fibonacci and the golden ratio, these concepts from afar might seem very different, but they are like extremely linked ideas in math. And there's so much more that I can say about these topics, but I might save those for other videos. But yeah, thanks for watching. Cheers.